Tonight we're going to reckon with a number that sounds almost manageable and isn't. In August 2016, astronomers confirmed a rocky planet orbiting the nearest star to our Sun. Rocky in the habitable zone. Mass close to Earth's, the star it circles, Proxima Centauri, is just 4.24 light-years away. Most people assume that nearest means reachable, but compared to billions of light-years of observable universe, 4,024 light-years is practically a short hop. By the end of tonight, you'll understand exactly why that assumption is wrong, and why the reasons stack so completely that physicists use one specific word for what separates us from Proxima b. If sitting with the hardest questions in science is what brings you here, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The announcement came on August 24th, 2016, and for a few days it felt like the question had been answered. A team led by astronomer Giamanglada Eskard at Queen Mary University of London had been collecting data for years from an instrument called HARPS, the High Accuracy Radial Velocity Planet Searcher, mounted on a telescope in Chile's Atacama Desert. HARPS does one thing. It detects the gravitational wobble a planet induces in its host star as it orbits. Not the planet itself. The wobble. A star tugged back and forth by something circling it, its light shifting fractionally bluer as it moves toward us, fractionally redder as it moves away. The wobble they found was 1.4 meters per second. Let that land for a moment. Not 1.4 kilometers, not 1.4 miles, meters per second. A brisk walking pace, detected across 25 trillion miles by reading the color of starlight through a spectrograph in a desert. The signal repeated every 11.2 days. A planet, rocky, with a minimum mass of at least 1.07 times Earth's, orbiting inside the habitable zone, the range of distances where a star's warmth could allow liquid water to sit on a surface. At Proxima Centauri, the nearest star to our Sun. What the team had found was not just any exoplanet. Thousands had already been catalogued by then, scattered across the galaxy at distances of hundreds to thousands of light-years. What they had found was the closest possible world to Earth. If you left the solar system in the direction of Proxima Centauri, this planet would be the first thing you encountered. Rocky, in the right temperature zone, at the right size, at the nearest star. In the days after the announcement, the story ran everywhere, not in science publications alone, in the kind of newspapers that rarely cover astronomy at all. Because the discovery required no technical background to understand. A planet at the nearest star. That's it. That's the whole thing. There are problems with it, of course. There are many problems with it. They do not announce themselves immediately. But the planet is real. That part never changes. Proxima b orbits its star every 11.2 days, has done so for approximately 4 billion years, and will continue doing so long after every living thing on Earth is gone. We found it. We measured it from here, from one small planet, without sending anything anywhere. The address is confirmed. The radial velocity method that revealed Proxima b is one of the detection techniques used to discover thousands of exoplanets, but it works with particular reliability on nearby stars where the signal to noise is favourable. The Doppler shift that HARPS measures, the fractional compression and stretching of spectral lines as the star moves toward and away from us, requires a spectrograph calibrated to a precision that engineers in the 1990s thought was beyond reach. HARPS achieves a velocity precision of approximately 1 meter per second. That means detecting, from Earth, a star moving at walking speed across the interstellar void. The instrument is a genuine achievement of precision engineering. The difficulty of extracting the Proxima b signal from the HARPS data deserves emphasis. Red dwarf stars like Proxima Centauri are intrinsically variable. They show radial velocity variations driven by stellar activity, spots, convective motions, and flare events that create signals in the spectrum that can mimic planetary signatures. Disentangling a planet's gravitational signature from a star's own behaviour requires years of observations across many stellar rotation cycles, sophisticated modelling of the stellar activity, and careful statistical analysis. Anglada Eskard's team used data from HARPS combined with archival data from other instruments going back over a decade. The signal they found had to survive a rigorous attempt to explain it as stellar noise rather than a planet. It survived. The planet is real. The planet Anglada Eskard's team found at 4 meters per second has been confirmed by independent groups using different instruments, different datasets, and different analysis methods. The confirmation is solid. There is no serious scientific dispute about Proxima b's existence. What is disputed, what remains genuinely unknown, is what Proxima b actually is like. Whether it has an atmosphere, whether that atmosphere could support liquid water, whether the surface is rock or ice or something we do not have a good comparison for, whether anything moves on it. These questions, which matter enormously for any assessment of the planet's value as a destination, are questions for future instruments, not settled science. The distance to that address is what this script is about, not in the abstract sense of space is big and stars are far. In the specific sense, what would it physically take to cross that gap? What barriers exist in the path? And why those barriers combine into something that physicists, when they are being precise, describe with one word that the title of this script already used. That word is not used loosely here. It will be earned over the next several chapters, one layer at a time. 4.24 light-years sounds like almost nothing. That is the problem. The human brain did not evolve to handle interstellar distances. It evolved to track prey across a savanna, to navigate between watering holes separated by tens of miles, to understand distances that legs could cover. Numbers work fine at the scales we evolved for. Beyond certain thresholds, the arithmetic continues to function, but the intuition disconnects from it. A number like 25 trillion miles is not processed by the brain as a felt quantity. It is stored as a symbol that represents something very large, and the brain files it alongside other very large numbers without registering the differences between them. 25 trillion and 25 billion produce roughly the same emotional response, even though one is 1,000 times larger than the other. This is not a personal failing. It is a universal feature of human cognition. Scientists who work with astronomical scales spend years developing intuition for numbers the brain was not built to handle, and even they report that the intuition remains effortful, a practiced skill rather than a felt reality. The distances in this script are real numbers, confirmed by they are not estimates or approximations. The feeling that they should be more manageable than they are is an artifact of being a human being, not a property of the distances themselves. 1 light-year is the distance light travels in a full year, moving at 186,282 miles per second. In 1 second, light circles Earth 7.5 times. In 8 minutes and 20 seconds, it crosses the 93 million miles from the Sun to us. In 1 full year of travel at that speed, light covers 5.88 trillion miles. Proxima Centauri sits 4.24 of those years away. In miles, that is just under 25 trillion miles. Now consider what 25 trillion miles actually means as a distance. The circumference of Earth at the equator is 24,901 miles. If you stacked Earth's circumferences end to end, 1 billion of them, you would have laid out approximately 24.9 trillion miles. Proxima Centauri is roughly 1 billion Earth circumferences away from us. If you drove there at highway speed, 65 miles per hour, never stopping, the trip would take approximately 50 billion years. The universe itself is only 13.8 billion years old. You would need to start driving before the Big Bang and still not have arrived. Sit with that for a moment. When the light now entering your eyes from Proxima Centauri left that star, it was 2021. What you see when you look at Proxima is not what it looks like. It is what it looked like 4 years ago. The planet has completed more than 130 orbits since then, and you would have no way of knowing what happened during any of them. That 4-year delay is built permanently into every observation we ever make of that system. It is not a limitation of our technology, it is the universe telling us the rules. Proxima Centauri itself is a red dwarf, a dim star with about 12% of the Sun's mass, producing roughly 0.17% of its light output. It cannot be seen without a telescope despite being the nearest star to us, which is why astronomers missed it entirely until 1915. When Robert Innes in Johannesburg noticed its motion across the sky and measured its distance. A star so close it went unnoticed for the entirety of recorded human history. It may be gravitationally bound to the Alpha Centauri binary, two Sun-like stars, A and B, locked in an 80-year mutual orbit, with Proxima as a faint distant companion, the three of them moving through space together. The exact nature of that bond is still being refined. There is something worth sitting with in the fact of Proxima Centauri's invisibility to the naked eye. The closest star to our Sun, the nearest point of the stellar neighbourhood we inhabit, was unknown to every human civilization that preceded the 20th century. Every astronomer who ever lived before 1915, from Hipparchus to Galileo to Newton to Herschel, had no idea it existed. It is there in every sky that was ever observed from this planet, producing too little light to register without modern instruments. The nearest thing is sometimes the hardest to see, but the key number is 4.24. 4.24 light years, 25 trillion miles, 1 billion Earth circumferences. Here is one more way to feel it. Light that left Proxima Centauri when you were born is only now reaching you. If you are in your mid-20s, the light entering your eyes from that star right now left the system before you existed. The star you are looking at, if you could see it, is not the star as it is. It is the star as it was when your parents were younger than you are now. Every observation of any star is an observation of the past. The closer the star, the more recent the past, and even the nearest star to our Sun is still 4 years back in time. This is not a poetic exaggeration, it is the actual structure of what observation means at interstellar distances. You can only know Proxima Centauri as it was. You will never know it as it is. The delay is irreducible, permanent, and equal in both directions. The information travelling to you is as delayed as any information you might send back. The nearest star to our Sun is not near. It is simply the least far away, and those two things are not the same. The fastest object humanity has ever built is out there right now, moving through interstellar space. Voyager 1 launched on September 5th, 1977. It swung past Jupiter in 1979, Saturn in 1980, collected data from both, and then kept going. It crossed the heliopause, the boundary where the Sun's influence gives way to true interstellar space, in 2012. It is still transmitting, still returning data. After nearly 5 decades of continuous flight, It is the most distant human-made object in existence. It travels at approximately 38,000 miles per hour. At that speed, Voyager 1 would take roughly 73,000 years to reach Proxima Centauri. 73,000 years. 73,000 years ago, anatomically modern humans existed. We had language, probably. We made stone tools. We were beginning to spread out of Africa. We had no agriculture, no permanent settlements, no writing, no mathematics, everything that separates the world you were born into from the world of our earliest ancestors. Every civilization, every city, every technology, every piece of accumulated knowledge happened in the time it would take Voyager 1 to reach the nearest star. The Parker Solar Probe holds the current speed record for any spacecraft. At its closest approach to the Sun, it reaches approximately 430,000 miles per hour, the fastest any human-made object has ever moved, more than 10 times faster than Voyager. At that speed, the trip to Proxima b would take approximately 6,700 years. 6,700 years ago, the oldest writing systems were being developed in Mesopotamia. The pyramids of Giza had not yet been built. Bronze Age civilization was just beginning in parts of the world, while much of humanity was still living in ways that would be recognizable to their ancestors of 10,000 years prior. Agriculture had been practiced for only a few thousand years. No city had yet built a wall. The wheel was new. A Parker Solar Probe launched today, the fastest object humanity has ever built, would arrive at the nearest star in the same era that is separated from us by that entire arc of human history. If the Parker Solar Probe had launched when the first city was being built in Mesopotamia, it would be arriving approximately now. That is what 6,700 years means. That is the fastest thing we have ever built, applied to the nearest star. Here is what that number does not say. The Parker Solar Probe was not designed for interstellar travel. Neither was Voyager. These are the fastest machines we have ever built, and they are tools for exploring our solar system, not crossing the void between stars. What they demonstrate is the gap between what we are capable of and what reaching Proxima b would actually require. In 47 years of continuous operation, Voyager 1 has covered roughly 14.5 billion miles. Proxima Centauri is 25 trillion miles away. Voyager has travelled in its entire operational lifetime about 0.06% of the distance to the nearest star. That is where we are. There is a way to feel this number that arithmetic alone cannot produce. Consider what the radiation environment beyond the heliopause actually is. Inside the solar system, the Sun emits a constant stream of charged particles, the solar wind, that fills the space between planets and, more importantly, creates a bubble of lower energy density that deflects some fraction of the galactic cosmic rays trying to enter. This bubble, the heliosphere, is itself a kind of radiation shield. Not an effective one against the most energetic particles, but a partial one. Beyond the heliopause, the boundary Voyager 1 crossed in 2012, that partial protection ends. The galactic cosmic ray flux increases. The most energetic particles, which penetrate spacecraft hulls and biological tissue regardless of the heliosphere's influence, are present everywhere in the interstellar medium. There is no shelter. The interstellar medium is not vacuum in an absolute sense. It contains gas and dust at extremely low density, and at interstellar cruise velocities, even these tenuous particles impact with significant energy. A grain of dust roughly the size of a human hair, struck at 10% of light speed, delivers energy comparable to a bullet. Over decades of cruise, cumulative impacts erode surfaces, compromise thermal protection, and degrade materials in ways that cannot be inspected from inside the ship. Voyager 1 has been operating for nearly 50 years. The engineers who designed it, who optimized its trajectory, who selected which instruments to include and how to configure the guidance system, are mostly retired now or gone. The spacecraft they built outlasted many of them. It continues to transmit, continues to function, continues to move through a space no human-made object had ever entered before it, and in the nearly 50 years it has been doing this, it has crossed less than 0.1% of the distance to the nearest star. The machine is extraordinary. The gap is larger. The engineers who built Voyager 1 designed it to operate for 4 years, long enough to complete the grand tour of the outer planets that a rare planetary alignment made possible in the late 1970s. They used radiation-hardened electronics and redundant systems, knowing the spacecraft would pass through the intense radiation belts around Jupiter and Saturn. They calculated trajectories using slide rules and early computers in an era when email did not exist, and the internet was a research project. The spacecraft they built has now operated for nearly 50 years. It has survived distances, temperatures, and particle environments its designers could not fully model. It is a monument to what careful engineering can produce. And it has covered 14.5 billion miles. Proxima Centauri is 25 trillion miles away. These two numbers exist in the same universe governed by the same physics. The ratio between them is not an engineering problem. It is a statement about the scale of the gap between where human technology currently operates and where the nearest star is. Voyager was not a failure at interstellar travel. It was never designed for applying its performance as a measure of what would be needed to reach another star is like measuring ocean distances with a ruler designed for desk drawers. The obvious move is to build something faster. And the options are real. Chemical rockets, every crewed mission in history, work by burning fuel and expelling the exhaust. The efficiency measure is called specific impulse. The best chemical engines achieve around 450 seconds of specific impulse. This is the ceiling. After 70 years of refinement, chemical propulsion is at its limit. The math compounds against you. Fuel has mass, which requires more fuel to move, which has more mass, which requires still more fuel. The rocket equation, worked out by Konstantin Tsiolkovsky in 1903, captures this spiral precisely. For interstellar distances, chemical propulsion is not slow. It is simply the wrong category of technology. Nuclear thermal propulsion doubles the efficiency. A reactor heats liquid hydrogen to extreme temperatures and expels it through a nozzle. The Nerva program demonstrated working engines in the 1960s. The technology worked. It was cancelled for political reasons, not engineering ones. With nuclear thermal propulsion, the trip to Proxima b would fall to somewhere between 25,000 and 40,000 years, still measured in the entirety of recorded human history, multiplied several times over. Nuclear pulse propulsion goes further. Freeman Dyson and Stanislaw Ulam developed the concept in the 1950s under Project Orion, a spacecraft detonating nuclear explosions behind a pusher plate, riding each shockwave forward. Theoretical velocities of 3 to 10% of the speed of light have been calculated. At 3% of light speed, the transit to Proxima b takes roughly 140 years. At 10%, closer to 43 years. These numbers are qualitatively different. They move the mission from geological time into historical time. Dyson himself, one of the most rigorous physicists of the 20th century, believed that a modified Orion drive could reach nearby stars within a human generation. He was not a dreamer in the pejorative sense. He was a mathematician who had worked on the Manhattan Project and understood what nuclear energy could actually produce. His calculations were sound. The concept was real enough that the US Air Force funded a project development phase in the late 1950s before the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, effectively ended the program. What Project Orion demonstrated is that the idea of nuclear pulse propulsion is not science fiction. It is constrained not by physics, but by political and ethical decisions we have made about nuclear weapons. The treaty that banned it was probably the right decision. But as an engineering concept, as a proof that human civilization could, if it chose to, build something that moved at a few % of light speed, Project Orion represents a real data point in the propulsion ladder. And then there is fusion. Controlled nuclear fusion, the same process that powers the sun, could in theory propel a spacecraft to a significant fraction of light speed with a manageable fuel load. Theoretical transit times to Proxima b under fusion propulsion are estimated, depending on the design, somewhere between 50 and 100 years. Within a single human lifetime, barely at the optimistic end. But no fusion rocket has ever been built. No prototype exists. No laboratory has yet produced more energy from fusion than it consumed. The physics are sound. The engineering is a different matter entirely. We have been working on fusion for 70 years. It remains, as the joke goes, always 30 years away. The National Ignition Facility at Lawrence Livermore achieved fusion ignition in December 2022, producing more energy from a fusion reaction than the lasers delivered to the target, for the first time in history. That milestone was real and significant. A fusion rocket for interstellar travel requires sustained fusion at a scale and efficiency many orders of magnitude beyond what NIF demonstrated. The gap between those 2 points is where the engineering lives. The ladder is real. Each rung represents genuine physics. The problem is where the ladder ends. With the most ambitious propulsion technology we can currently theorize, not build, theorize, the trip to Proxima b still takes longer than a single human lifetime. A crew launched under the most optimistic fusion scenario would not arrive. Their children might not arrive, their grandchildren might, if everything held together across generations and the ship maintained its purpose across a century of isolation. That is the ceiling. You might be thinking, technology improves. That is a fair point. It always has. The Wright brothers flew 120 feet in 1903. 66 years later, humans walked on the moon. If the same rate of progress applies to propulsion, perhaps the ceiling lifts within a century or two. The challenge with that comparison is that the Wright brothers were not constrained by fundamental physics. Aerodynamics has room to maneuver. Propulsion at the interstellar scale is constrained by the rocket equation, a mathematical relationship worked out by Tsiolkovsky in 1903 that does not improve with time. Fuel has mass. Mass requires fuel to move. The relationship is exponential and merciless. Even if fusion propulsion is eventually built, even if it works at theoretical efficiency, even if the engineering problems that have resisted solution for 70 years are all resolved, the transit still takes longer than a human lifetime. The ceiling is not a ceiling we have not yet reached. It is one we have calculated from the laws of physics, and that is before we have discussed what happens to the people inside the ship. Long before the propulsion ceiling, the human body starts failing. This is not speculation, it is measurement. The International Space Station has been continuously inhabited since November 2000, and everything that happens to an astronaut in orbit has been studied, documented, and quantified. The data is specific, and the data is sobering. Bone density decreases at approximately 1 to 2% per month in the weight-bearing bones, the lower spine, the femur, the pelvis, not from disease, not from injury, from the simple absence of gravity demanding that the skeleton support weight. The body is efficient, it does not maintain what it does not need. Studies document this across multiple astronaut cohorts with bone density scans before, during, and after missions. 2% per month. 6 months in space, 12% gone from the spine. A year, more than 20%. That is not recoverable in a few weeks of physical therapy. That is the kind of loss that permanently changes how a person moves. IS astronauts exercise for approximately 2 hours every day specifically to fight this. The regimen is intensive, resistive exercise against specialized equipment designed to simulate load-bearing, cardiovascular training, protocols developed over decades of trial and refinement. The exercise slows the bone loss. It does not stop it. Returning astronauts still show measurable bone density deficits even after rigorous in-flight exercise programs. The best countermeasures we have developed, applied by healthy and motivated professionals in a well-resourced environment, do not fully compensate for the absence of gravity. On a mission lasting decades, the accumulated loss from even a slowed rate compounds beyond the threshold at which bones reliably support a body working in gravity. A crew arriving at Proxima B after 50 years, assuming the mission succeeded in every other respect, might not be able to stand on the planet's surface. The body that left Earth in one gravitational environment would arrive at another, changed by the decades between them in ways that exercise protocols developed for 6-month missions may not adequately address. Muscle atrophy tracks the same pattern. Without the constant demand of working against gravity, muscle mass declines. The heart is a muscle. In microgravity, the cardiovascular demand of pumping blood upward against a gravitational gradient disappears. Echocardiograms on returning IS crew members show measurable changes in cardiac geometry. The heart in practice reshapes itself. Mostly recoverable. Mostly, spaceflight-associated neuroocular syndrome has emerged from long-duration mission data as one of the more concerning findings of the past decade. Roughly 40 to 60% of long-duration IS astronauts develop it. The exact proportion varies across studies. In microgravity, fluid redistributes toward the head. Intracranial pressure rises. The optic nerve sitting in that increased pressure undergoes structural changes. Some astronauts return with permanently altered vision. The mechanism was not understood or even clearly identified for most of the IS program's early years. It took years of cumulative data to recognize it. The immune system drifts. Latent viruses that sit dormant in healthy people, Epstein-Barr, cytomegalovirus, varicella zoster, reactivate at higher rates during spaceflight. The microbiome inside the ship converges as people share a closed environment, narrowing the diversity of immune challenges the crew experiences. Over decades, these changes accumulate in ways we have never studied because no human being has ever spent decades in space. Now consider what any of this means for a mission lasting 50 to 100 years. The longest single spaceflight in history was Valery Polyakov's 437 days aboard Mir in 1994 and 1995. At landing, he was carried from the capsule. He could not walk. Rehabilitation took months, and he was a healthy, elite cosmonaut in peak physical condition at departure. At 100 years, at a mission requiring the body to function well enough to land on a planet, work a surface, and possibly return. There is no precedent, no data, and no basis for optimism. What about cryosleep? No functional human cryopreservation technology exists. Early-stage medical research explores metabolic suppression for short emergency applications, minutes, not months. There is nothing at any stage of development that approaches decades-long preservation of a human being, and radiation, which we will get to shortly, does not stop accumulating because the body is unconscious. Scott Kelly, who spent 340 days aboard the ISS in 2015 and 2016, returned measurably different from his twin brother Mark, who had not been in space. The comparison was the subject of a NASA study, the first study to systematically examine the effects of long-duration spaceflight on the human body by comparing an astronaut to a genetically identical control. The results were specific. Gene expression patterns had changed. Scott's telomeres, the protective caps on chromosomes, had lengthened in space and then shortened rapidly upon return. His gut microbiome had shifted. His cognitive performance on certain tests had changed. Most effects were reversible, some were not. 340 days. A mission to Proxima b at the optimistic fusion propulsion timeline takes 50 to 100 years. The ratio of those durations to Kelly's record-setting mission is between 54 and 108 to 1. We have no data from anything within 2 orders of magnitude of the required duration. We are extrapolating into territory where extrapolation is itself uncertain. The body that leaves Earth for Proxima b, under any propulsion scenario we can build, will not be the body that arrives. What would 50 years in microgravity actually look like? We have no data for it. The longest any human has spent in space is 437 days. Beyond that, we are extrapolating, using the known rate of bone loss, the documented cardiovascular changes, the measured decline in muscle mass, the recorded immune system alterations, and projecting those rates forward into a duration no human body has ever experienced. The projection is not encouraging. At 2% bone density loss per month, compounded across 50 years without perfect countermeasures, the skeleton does not function. At the cardiovascular change rates documented in long-duration ISS crews, the heart has been reshaped. At the vision impairment rates documented in the neuroocular syndrome literature, some crew members may not have useful vision by the time they arrive. The people who would step onto the surface of Proxima b if the ship held together and the mission succeeded. They would arrive as passengers in bodies that the transit had spent 50 years modifying without consent. Outside the protection of Earth's magnetic field, space is not empty. It is full of particles moving at near light speed, arriving from every direction, passing through metal and flesh as if neither one existed. Galactic cosmic rays are atomic nuclei, mostly protons, with helium nuclei and heavier ions including iron, accelerated to extreme energies by supernovae, neutron star collisions, and the relativistic jets of distant active galaxies. They arrive from all directions because the galaxy's own magnetic field has scrambled their paths over millions of years of travel. They carry energies that, at the high end, exceed anything produced by any particle accelerator on Earth. At these energies, they do not behave like conventional radiation. Lead shielding stops X-rays. It does not stop galactic cosmic rays. When a high-energy cosmic ray strikes dense material, it initiates a cascade of secondary particles, protons, neutrons, muons, gamma rays that spreads the dose rather than absorbing it. Adding shielding beyond a certain thickness actually increases the secondary particle shower reaching the interior. The intuitive fix makes the problem worse. Earth's magnetic field deflects incoming cosmic rays before most of them reach the surface. It works at planetary scale, a magnetic bubble extending thousands of miles into space, bending particle trajectories around the planet. At this altitude, still inside this protection, astronauts receive approximately 150 millisieverts of radiation per year. In interplanetary space, that protection is gone. The Curiosity rover carried a radiation detector during its transit from Earth to Mars in 2011 and 2012. The radiation assessment detector measured an average dose rate in interplanetary space of approximately 8 millisieverts per day, around 650 millisieverts per year, more than 4 times the IS annual dose outside the magnetosphere in the space between planets. These measurements were taken in the inner solar system, within the heliosphere, during a period of moderate solar activity. They represent a realistic assessment of what a crew would experience during an interplanetary transit, not during a solar energetic particle event, which can spike radiation doses dramatically over hours, and not in the interstellar medium beyond the heliopause, where the galactic cosmic ray flux is higher still. The Curiosity numbers are a floor, not a ceiling. Actual dosimetry on a long-duration interstellar mission would likely be significantly worse. For reference, the average annual radiation dose for a person living at sea level on Earth is approximately 3 millisieverts per year, combining background radiation, medical imaging, and other sources. Interplanetary space delivers more than 200 times that annually. In 50 years of interplanetary transit, the optimistic fusion propulsion timeline, a crew would accumulate a dose that exceeds the annual Earth background rate by a factor of more than 10,000. NASA's career exposure limit for astronauts, set to cap lifetime excess cancer risk at 3%, runs to roughly 600 to 1200 millisieverts total, depending on age and biological sex. A crew member would exhaust their entire permitted lifetime dose in under 2 years of interplanetary travel. The trip to Proxima B at fusion propulsion speeds takes 50 to 100 years. The obvious solution is shielding. More mass around the crew compartment, more material to absorb incoming particles. But here is what that solution does not say. More mass means the ship is heavier. A heavier ship requires more propulsion energy to accelerate. More energy means either more fuel, which adds more mass, or accepting a lower final velocity. Lower velocity means a longer mission. A longer mission means more time exposed to radiation. More exposure time means a higher total dose, partially offsetting the protection the added shielding was supposed to provide. The shielding paradox is self-reinforcing. Every fix that reduces the dose increases the mass. Every increase in mass increases the transit time. Every increase in travel time increases the dose. The variables are coupled in a loop that has no clean exit. Active magnetic shielding, generating an artificial magnetosphere around the spacecraft, has been proposed as an alternative. The physics of the power requirements for a field strong enough to protect a crew against galactic cosmic rays across a meaningful volume of space are enormous, and the engineering has never been attempted at anything approaching the required scale. There is no currently proposed solution to the radiation problem that fits on a spacecraft and works across decades of interstellar travel. There is a strange wonder in the source of these particles. The galactic cosmic rays that would damage a crew's DNA during an interstellar transit are, many of them, products of the most dramatic events in the universe. Supernovae, neutron star mergers. The relativistic jets of black holes swallowing matter at the centers of galaxies billions of light years away. The particles that make interstellar space dangerous to human biology have crossed unimaginable distances, accelerated by unimaginable events, and they carry in their trajectories a record of processes occurring across the full breadth of the observable universe. The same cosmic violence that seeded the interstellar medium with heavy elements, including the carbon and iron and calcium that make up every human body, also fills that medium with radiation that would, over the timescale of a mission to Proxima b, systematically destroy any unshielded living thing trying to cross it. The universe provides both the material for life and an environment hostile to it. This is worth being precise about, because proposals exist. They are real proposals from real physicists. The question is not whether anyone has thought about the problem. It is whether any proposed solution works at the required scale, across the required duration, with the mass and power budgets a spacecraft can realistically carry. Liquid hydrogen, which makes excellent shielding against certain particle types, adds enormous mass and requires cryogenic storage, adding complexity and failure modes to a system that must work without maintenance for decades. Water shielding is effective against lower energy cosmic rays, but does not adequately address the most energetic particles. Polyethylene and other hydrogen-rich polymers provide some benefit, but not at the thickness required for long-duration protection without unacceptable mass penalties. And none of these materials addresses the secondary particle cascade problem, the fact that dense above a certain thickness creates more harmful secondaries than it blocks. The radiation problem for an interstellar mission is not unsolved because no one has worked on it. It is unsolved because the physics of high-energy galactic cosmic rays are genuinely hostile to the mass and volume constraints of any spacecraft we could build. Consider what a crewed spacecraft to Proxima b actually requires, not as a vision, but as an engineering list. Air, recycled continuously, with oxygen replenished and carbon dioxide removed at near perfect efficiency for decades. Water recovered from urine, sweat and condensation through processing systems that cannot fail because there is no resupply. Food, grown or stored or both, across a century of isolated operation with no access to external agricultural expertise when something goes wrong with the crops. Heat maintained against the cold of interstellar space, with power systems that must function without maintenance from any manufacturer on Earth. Medicine, for conditions that arise without warning, treated by crew members without access to specialists or hospitals or replacement drugs. Structural integrity, maintained against micrometeorite impacts that accumulate over decades with no dry dock, no external inspection possible, no hull damage accessible from inside. Each of these items is a separate engineering problem of substantial difficulty, but they are not independent. The oxygen the crew breathes is produced by the water electrolysis system, which requires power. The power comes from the reactor, which requires maintenance by people who understand nuclear engineering at a deep level, not just procedurally, but mechanistically. The food grown in the ship's agricultural section requires light, which requires power, and soil or hydroponic medium that must maintain chemical balance across decades without the input of nutrients that agriculture on Earth takes from an effectively infinite reservoir. Waste from the crew, biological and material, must be processed and returned to the system, because nothing can be discarded into space and replaced from outside. Closed ecological systems, artificial biospheres that recycle all matter and require only energy input, are extraordinarily difficult to maintain, even with external engineering support. The Biosphere 2 experiment in Arizona attempted this at small scale, with 8 people for 2 years, with full access to outside expertise and supply chains if the experiment failed. It did not meet its own targets. Oxygen levels dropped. Food production fell short. The crew supplemented from stored provisions. The experiment was instructive, but not in the direction its designers hoped. No closed ecological system in human history has achieved the efficiency and reliability a multi-decade interstellar mission would require. The International Space Station is the most sophisticated life support system humanity has ever operated in space. It has been continuously inhabited for over 25 years. It weighs approximately 420 metric tons, it supports 6 people, and it depends on Earth continuously. Cargo missions arrive roughly 4 to 5 times per year. Food, spare parts, water supplementing the recycling system, replacement components for systems that have failed. When the oxygen generation assembly breaks down, engineers on the ground diagnose it through telemetry, work out a repair procedure, and walk the crew through it in near real time. When the water recovery system needs a filter change, the filter arrives on the next resupply vehicle. The ISS has never been self-sustaining. It has never needed to be. A spacecraft to Proxima b needs to be self-sustaining. Completely, permanently, for a century. Current best-performing closed-loop life support prototypes recover approximately 90 to 95% of water through urine processing and condensation recovery. For a 6-month mission, the shortfall is manageable with reserves. For a decade-long mission, the accumulated loss exceeds the carrying capacity of any practical reserve. For a century, anything less than near-perfect recovery is a death sentence. Now consider reliability mathematics across that duration. A critical system, oxygen generator, water recycler, carbon dioxide scrubber that has 99% probability of avoiding catastrophic failure in any given year has a 37% survival probability across 100 years. That is a 63% chance of catastrophic failure from a single system with no replacement parts and no repair support from Earth. A crewed spacecraft to Proxima b has dozens of critical systems. The probability that all of them survive without catastrophic failure for a century simultaneously with no external support is not a number that any mission planning process can work with. That is where engineering stands today. This is not a criticism of the engineers. The ISS life support systems represent extraordinary achievements. The water recovery system that processes urine and condensation into drinking water, the oxygen generation assembly that electrolyzes water, the carbon dioxide removal system that scrubs the atmosphere, all of these work. They work reliably, in space, under conditions that challenged every engineering assumption made on the ground. The people who built and maintain them are among the most skilled engineers alive, but the ISS works because Earth is there. Not abstractly there as a comforting concept, but practically there as a supplier of replacement parts, a facility for engineering support, a source of resupply for everything the recycling system loses. The gap between life support that works with regular resupply and repair and life support that works without any external input for a century is not a gap of engineering refinement. It is a gap of fundamental approach. Nothing we have built has ever had to do the second thing. There is a proposal that sounds like the answer. It is real. It is funded. It has the backing of serious physicists. Breakthrough Starshot was announced in April 2016, weeks before the discovery of Proxima b. Funded by Yuri Milner, with Stephen Hawking among its public supporters, the project proposes this: build an enormous ground-based laser array. Use it to accelerate a gram-scale spacecraft, a nanocraft mounted on a light sail, to 20% of the speed of light. At that speed, the trip to Proxima Centauri takes approximately 20 years. 20 years. Not 73,000. Not 6,700. 20 within the career of the scientists who proposed it. Within living memory. This sounds like the escape hatch the previous chapters do not have. Here is what that number does not say. The nanocraft weighs approximately 1 gram. 1 gram is a paperclip. A raindrop. At that mass, the laser can accelerate the sail to 20% of light speed within a feasible array power budget. Increase the payload substantially to carry a human being, life support, food, water, radiation shielding, navigation systems, deceleration hardware, and the energy required scales prohibitively. A crewed vehicle is not what Breakthrough Starshot can accelerate. It was never designed to be. There is also no deceleration mechanism. A nanocraft travelling at 20% of light speed, 134 million miles per hour, has no way to slow down at the destination. The laser that pushed it forward is still on Earth, 20 years behind it. There is no onboard fuel. The design's entire logic depends on carrying no propellant. The spacecraft arrives at the Proxima Centauri system and passes through it. It does not orbit, it does not descend, it does not land. It traverses the entire inner system, from the outer boundary to past Proxima B's orbit, in approximately 4 to 5 hours, its cameras firing, its transmitters beginning a signal that will take 4.24 years to reach Earth. A postcard. Not a mission, no crew, no stop, no landing, no return. And the images it captures at those speeds and that transit time will be blurred beyond the resolution of useful science. The engineering challenge of capturing meaningful data in a 4-hour flyby at relativistic velocity is itself unsolved. Breakthrough Starshot is a genuine scientific project working on real engineering problems, laser coherence, sail material, miniaturized instruments. It may one day send a gram-scale probe that photographs a star system and transmits the images back. The closest analogy in the history of space study is New Horizons, a small spacecraft sent to photograph a previously unvisited world during a single flyby. New Horizons reached Pluto in 2015 after 9.5 years of travel, photographed it during a close approach lasting and transmitted data back across 5 billion kilometers. That data took 16 months to fully download. The scientific return was extraordinary. A previously blurry smudge became a mapped world. What Breakthrough Starshot would do at Proxima B is similar in structure and incomparably harder in execution. A flyby at 20% of light speed. Instruments that must function after 20 years of interstellar cruise. A transmission from 4.24 light-years away from a gram-scale transmitter. Every element of that chain is at or beyond the edge of current engineering. But none of that is the reason it cannot carry humans. It cannot carry humans because the physics of laser propulsion at this efficiency require gram-scale payloads. That is the constraint. What it cannot do, by design, is carry a human being to Proxima B. The escape hatch closes. If no single crew can survive the transit, the oldest solution is to accept that. Send enough people to have children. Their children have children. The mission continues across generations until someone, descended from the original crew, born in interstellar space, never having seen Earth, arrives at Proxima B. The generation ship is science fiction's most durable solution to interstellar distance. It also has the most problems. Start with genetics. A founding population that is too small will face genetic bottleneck effects over generations, harmful mutations accumulating, recessive conditions expressing, adaptive capacity narrowing. Researchers who have studied minimum viable population sizes for isolated populations disagree on the number. Some studies suggest several hundred can be managed under careful reproductive oversight. Others, accounting for realistic reproductive variation and random genetic drift across centuries, push the minimum into the low thousands. The honest range across published literature is somewhere between a few hundred and over 1,000, with no settled consensus. Whatever the number, they need to be supported. The ship must grow enough food for the full population, recycle all their water, manage all their waste, maintain their health, educate their children, and sustain all of this across a century or more without external input, which returns us to the engineering problems of the previous chapter, now at greater scale and greater duration. But the deeper problem is social. No human civilization has maintained a single coherent institutional purpose across multiple centuries in complete geographic isolation. This is a statement about the historical record. The Roman Republic lasted roughly 500 years before transforming into something its founders would not have recognized, and it was never isolated, never closed, never cut off from outside input, trade, war, and the continuous friction of contact with other civilizations. The generation ship offers none of those inputs. It is sealed. It goes where it was aimed. The closest historical analogies we have are intentional communities, religious groups, utopian settlements, isolated colonies, and the record is not encouraging. The Pitcairn Island colony, established by the Bounty mutineers in 1790, descended into violence within a generation. The Biosphere 2 experiment in Arizona, designed in the early 1990s to test whether a sealed ecological system could sustain 8 people for 2 years, ended in conflict, management crises, and a scientific understanding that closed ecosystems are far harder to maintain than anyone anticipated. 2 years, 8 people in a sealed facility on Earth with full communication, access to outside expertise, and the ability to abandon the experiment if necessary. A generation ship needs to sustain hundreds or thousands of people for a century without communication, without resupply, without the option to leave. There is no historical model for this. There is no analogous human institution that has attempted it and succeeded. The generation ship concept is, at its heart, an assumption that something unprecedented is possible, based on no evidence that it is. The people who board the ship chose the mission. Their children did not. A person born 30 years into the voyage inhabits a world entirely defined by a decision made before their conception, a metal enclosure moving through the dark toward a destination they will not live to see, to fulfill an obligation placed on them by people who are now dead. The ethics of this situation do not resolve with better engineering. This is not a new problem. Children are born into circumstances they did not choose. Countries, religions, economic classes, family obligations, and philosophy has long debated the extent to which decisions made before a person's birth can ethically bind that person. But the generation ship intensifies every parameter of that question to an extreme that no terrestrial example approaches. A child born into poverty on Earth can, in principle, choose a different path. A child born on a generation ship has no path other than the one the ship is on. There is no other country to emigrate to. There is no institution outside the ship's governance to appeal to. There is no way to decline participation in the mission without declining to exist within the only environment available. The ship is not a circumstance the person was born into. It is the totality of their reality. Some philosophers who have considered this question argue that the potential significance of a successful mission, establishing a human presence at another star, opening the cosmos to the species, is sufficient to justify the constraint placed on the people born during transit. Others argue that no future benefit can justify creating people specifically to serve as instruments of a goal they did not choose. The debate is not settled. On a generation ship, it cannot be settled, because the people most affected by the outcome will be born after the ship has launched. Knowledge degrades. The technical systems keeping the ship alive require not just operators, but people who understand deeply enough why those systems work to improvise when something fails in a way the original designers did not anticipate. That understanding is transmitted through direct instruction and practice. Languages drift across centuries. The English of 1300 is not fully intelligible to a modern reader without study. A repair manual written in 2050 may, by the ship's 5th generation, require something approaching translation. The knowledge of Roman concrete, the specific mix ratios that produced structures lasting 2,000 years, was lost not because it was destroyed, but because the chain of practitioners who understood it broke. On a generation ship, that chain has no external reinforcement. Governance becomes its own crisis. Who commands? Who decides reproductive policy, resource allocation, mission parameters? Technical expertise must be balanced against the need for people to feel they have some say in their own lives. History offers no model of a governance system that maintained legitimacy across multiple generations in full isolation, because no such society has existed. A generation ship solves the propulsion problem by removing it. It is worth being clear about what solves means in this context. It does not mean the propulsion problem ceases to exist. A generation ship still needs propulsion. It must reach a fraction of light speed sufficient to complete the mission in a reasonable number of generations. 1% of light speed would take 424 years to reach Proxima b. More ambitious designs aim for 5 to 10%, bringing that down to 43 to 85 years. The propulsion system must then operate for that duration without maintenance. Solves means the propulsion requirement is reduced from fast enough for a single human lifetime to fast enough for several human lifetimes, which is still an unsolved engineering problem, but a less extreme one. Consider what this would feel like from the inside, not from the outside, as a mission planning exercise, but from the perspective of a person born on board in year 40 of the voyage. You have never seen a natural sky. You have never breathed unprocessed air. You have never stood in a space larger than the ship's largest common area. You have been told, all your life, that you are going somewhere. A planet at a star called Proxima Centauri, 4,024 light-years from a world called Earth. But you have no lived memory of either place. Earth is a story. Proxima b is a destination. The ship is all there is, and you are expected to maintain the ship, to learn the technical systems that keep it alive, to teach those systems to your children with the same accuracy with which they were taught to you, across a chain of transmission that stretches back to engineers who are now 4 decades dead and whose intuitive grasp of why things worked the way they did cannot be fully captured in any manual. What it puts in its place has never been solved by any civilization that has ever existed. Proxima Centauri is a red dwarf, the most common type of star in the galaxy, and one of the most violent. Red dwarfs account for roughly 70 to 75% of all stars in the Milky Way. They form more often than larger stars, and they live vastly longer. Proxima Centauri, with 12% of the Sun's mass, has a projected lifespan measured in hundreds of billions of years, far longer than the current age of the universe. In terms of sheer abundance and duration, red dwarfs dominate the galaxy. They also flare, not the way our sun flares, where a solar event disrupts satellite communications and produces aurora at high latitudes. Red dwarf flares are proportionally more violent relative to the star's own output, more frequent, and, critically, deliver this radiation to a planet orbiting far closer than Earth orbits our Sun. Proxima b orbits at 0.0485 astronomical units from Proxima Centauri. Earth orbits at 1 astronomical unit from the Sun. Proxima b sits at less than 5% of that distance. The reason it is in the habitable zone despite orbiting a dim star is that the habitable zone is proportionally closer to a dimmer star. The warmth works out. But the flares arrive at a planet that is 8 times closer to its star than Mercury is to our Sun. Observations of Proxima Centauri by the XME Newton X-ray Space Observatory and other instruments have documented superflares multiple times per year. During a superflare, the X-ray flux reaching Proxima b spikes to levels that studies estimate at roughly 400 to 800 times the X-ray dose Earth receives from our Sun during solar events, with the range depending on the specific modelling assumptions. What this does to an atmosphere is significant. A planet's atmosphere is continuously eroded by high-energy radiation and stellar wind. Earth retains its atmosphere partly because of its magnetic field, which deflects the stellar wind, and partly because of geological processes that continuously replenish atmospheric gas from the interior. Proxima b, orbiting far closer to a far more active star, faces an erosion rate many orders of magnitude more intense than Earth experiences. Whether Proxima b has retained a meaningful atmosphere depends on variables we have not yet measured, whether the planet has a magnetic field of its own, which depends on its internal structure and thermal history. Some models suggest atmosphere retention is possible. Others suggest the planet has been stripped to bare rock over billions of years of bombardment, and the flares do not arrive on a schedule. They are not predictable in the way weather can be predicted with a week's lead time. They occur on a statistical basis, frequently, but not at regular intervals. A crew on the surface during a period of stellar quiet might have weeks of relative calm, or hours. There is no safe season. There is no warning system that would operate reliably at 4 light-years of distance. The star that gives Proxima b its warmth also works, continuously, to strip away the conditions that would make that warmth useful. There is a useful comparison available. Our Sun produces powerful solar flares, events that can disrupt GPS systems, knock out power grids, and generate aurora as far from the poles as the mid-latitudes. The most powerful solar flare ever recorded, the Carrington event of 1859, disrupted telegraph systems worldwide and produced aurora visible in the Caribbean. If an equivalent event happened today, the disruption to satellite and electrical infrastructure would be severe. Proxima Centauri produces events of comparable or greater absolute energy from a star much smaller and dimmer than ours, directed at a planet orbiting nearly 20 times closer. The X-ray and ultraviolet flux during a superflare at Proxima b's orbital distance makes the Carrington event look like a normal day. Earth survives its flares because of distance and because of a global magnetic shield. Proxima b, if it lacks an equivalent shield, has neither advantage. In March 2016, just months before the discovery of Proxima b was announced, the Everyscope telescope array detected an extreme flare from Proxima Centauri. The flare increased the star's optical brightness by roughly 68 times its quiescent level. During this event, the EV flux at Proxima b's orbital distance was estimated to be sufficient to destroy NAR at the surface and to produce biologically lethal radiation doses over minutes of exposure. This was not an exceptional event. It was a superflare detected during a monitoring campaign, one of several documented superflares from Proxima Centauri in recent years. The frequency matters as much as the intensity. a single extreme solar flare on our Sun is rare, occurring perhaps a few times per 11-year solar cycle. Proxima Centauri produces superflares far more often. Monitoring campaigns have documented multiple large flares per year, with smaller flares on timescales of hours to days. A crew on the surface would not be managing the occasional extreme event against a background of calm. They would be managing a continuous, unpredictable radiation environment with periodic acute spikes, with no atmospheric buffer if the atmosphere has been depleted. The question of whether life could exist on Proxima b, despite this bombardment, is not settled. Biology on Earth has found ways to survive in extreme environments, deep in ocean vents, inside rocks, in highly acidic or alkaline conditions. Life underground or in the deep ocean, shielded from surface radiation, might be unaffected by stellar flares, but the planet's surface, the surface any landing crew would need to operate on, faces this radiation directly. Any surface mission, any habitat, any extravehicular activity would need to contend with a radiation environment that spikes unpredictably and without warning to levels instantly hazardous to unshielded humans. The star gives, the star takes away. It cannot do otherwise. At 0.0485 astronomical units from its star, Proxima b almost certainly does not rotate the way Earth does. The Moon always shows the same face to Earth. This is not a coincidence. Earth's gravity, acting over hundreds of millions of years on a slight asymmetry in the Moon's mass distribution, gradually slowed the Moon's rotation until its rotational period matched its orbital period. The Moon is tidally locked. One face always toward Earth. One face always away. Proxima b is in a far more extreme version of this situation. The gravitational gradient from its star at that orbital distance is enormous. The estimated timescale for tidal locking at 0.0485 astronomical units is tens to hundreds of millions of years, a small fraction of the planet's 4 billion year history. The consensus among planetary scientists who have studied the Proxima b system is that the planet is almost certainly tidally locked. What this means, one hemisphere faces its star permanently. One hemisphere faces the dark permanently. There is no day and night cycle. The star does not rise or set. One side of the world has seen unbroken daylight for 4 billion years. The other has seen unbroken darkness for 4 billion years. The atmospheric dynamics of such a world are unlike anything in our solar system. Temperature gradients between the two hemispheres drive powerful circulation, wind systems attempting to move heat from the hot side to the cold side. Under some models, this redistribution is sufficient to moderate both extremes, creating temperatures within ranges that could support liquid water somewhere on the surface. Under other models, the night side is cold enough that atmospheric gases freeze and fall to the ground, a scenario called atmospheric collapse, where the atmosphere gradually concentrates on the cold side as solid ice and the day side is stripped bare. Whether Proxima b avoids atmospheric collapse depends primarily on two factors: the planet's atmospheric pressure and whether it has maintained a thick enough atmosphere to allow meaningful heat transport. A planet with a thin atmosphere, like Mars, cannot transport enough heat across the terminator to prevent night side freezing. A planet with a thicker atmosphere, like Earth or Venus, can. The stellar flares discussed in the previous chapter bear directly on this question. Every superflare event strips some fraction of the upper atmosphere. Over 4 billion years of bombardment, the atmosphere Proxima b may once have had could be significantly depleted. The models disagree. The observational data to choose between them does not yet exist. Between these two extremes lies the Terminator, the great circle where day meets night, the strip of perpetual twilight where the star hangs fixed on the horizon, neither rising nor setting, for the entire history of the planet. If Proxima b has any habitable region at all, it is probably here. Temperatures might be temperate, atmospheric pressure might be stable. The star would illuminate this strip with a light that never changes, perpetual dawn that is also perpetual dusk, depending on which way you face. You do not know what morning means on a tidally locked world. There is no morning. There is no concept of the day beginning or the sky brightening, because the sky never brightens and never darkens. The most fundamental unit of time in human experience, the day, the rotation of the world through its own shadow, has no referent. Every human concept of time organized around celestial motion becomes meaningless. Circadian biology, shaped over hundreds of millions of years of evolution on a rotating planet, would face something it has never encountered. We looked for a planet that could support life. We found one at the nearest star. It is probably one hemisphere of frozen atmosphere and one hemisphere of relentless radiation, with a narrow habitable strip between them, where the sun never moves. That narrow strip, the Terminator, is interesting in a way that the rest of the planet may not be. Atmospheric circulation models suggest that heat transported from the day side to the night side by wind systems might create moderate temperatures along the Terminator band. Some researchers have argued that this eyeball planet configuration, named for the resemblance of the day-side hotspot to a pupil surrounded by the Terminator ring, could support liquid water in that ring despite the extremes on either side. This is not a comfortable vision of habitability. It is the least bad version of an alien environment where the constraints of orbital mechanics have produced something radically unlike Earth. No seasons, no weather patterns driven by rotation, no diurnal biology, no sunrise to organize a day around. A world where the star is a fixed feature of the sky, not a source of changing light that structures experience, but a permanent installation, like a light that was left on and cannot be turned off. The Terminator strip of Proxima b, if it is habitable at all, would be a place unlike any environment that produced the biology we know. It might support life, it would not produce life like us. The communication delay. If a crew reached Proxima b and encountered a problem, a failed landing system, an unexpected atmospheric reading, a medical emergency, the message describing that problem would take 4.24 years to reach Earth. A response would take another 4.24 years to return. 8.48 years. Round trip. The Apollo 13 crew, when an oxygen tank exploded 200,000 miles from Earth in April 1970, had a communication delay of approximately 1.3 seconds. In that environment, mission controllers in Houston could track telemetry in near real time, confer with engineers in the building, run simulation, and relay updated procedures to the crew within minutes. The improvisation that kept the crew alive, rerouting power, designing a CO2 scrubber from materials available on board, calculating a slingshot trajectory using the lunar module's engine, depended on continuous communication with a ground team that had access to the full intellectual and engineering resources of a modern civilization. The engineers on the ground during Apollo 13 included the people who designed the spacecraft. When the explosion happened and the telemetry showed a pattern no one had seen before, the designers were in the room. People who understood the system at the deepest level, who knew not just the procedures, but the underlying physics of why those procedures existed, could be consulted in minutes. 70 specialists worked the problem simultaneously, sharing information and coordinating responses in real time. That is what a functioning mission control looks like. That is what the 1.3 second delay permits. Now the explosion happens 4.24 light-years from Earth. The crew transmits a description of what the telemetry shows. 4 years and 3 months later, that description arrives on Earth. The engineers who designed the spacecraft are retired now, or gone. Their successors, who have never seen this failure mode before, read the transmission. They formulate a response and transmit it back. 4 years and 3 months after that, the response arrives. The crew has been managing the emergency alone for 8.5 years. Astronauts on the ISS today communicate with ground controllers effectively in real time. The physical separation of 250 miles introduces a delay of about 1.3 milliseconds. Mission controllers watch telemetry continuously. When a system shows anomalous readings, engineers on the ground catch it and flag it before the crew has noticed. Even a Mars mission, the farthest destination seriously discussed for human spaceflight, imposes a maximum one-way delay of approximately 24 minutes at greatest separation. Within an hour of any event on Mars, Earth can know about it and begin formulating a response. A Proxima B crew transmits a distress call. Earth receives it 4.24 years later. Earth sends a response. The crew receives it 4.24 years after that. If the emergency was acute, everyone involved has been dead for 8 years before the conversation completes. The communication delay is not a solvable technical problem. Radio waves travel at the speed of light. Laser communication travels at the speed of light. Quantum entanglement cannot transmit information faster than light. This is not a current technology limitation. It is a confirmed result of quantum mechanics with no known exception and no theoretical loophole that has survived scrutiny. Any signal from Proxima B to Earth travels at light speed, and light speed across 24 light-years takes 4.24 years. This is a permanent operational characteristic. A crew at Proxima B cannot be supported by mission control, cannot be rescued, cannot receive current medical advice for medical emergencies, cannot receive updated engineering guidance when something fails in a way the designers did not anticipate, cannot be redirected if the mission parameters need to. Every decision, permanently, entirely, would be made by the crew alone, with no recourse. They would be the most isolated human beings who ever lived. Not by a factor of 10 compared to the most isolated people on Earth. Not by a factor of 100. The nearest comparison, an Antarctic winter crew 6 months in near-complete isolation, still has satellite communication. Still has the knowledge that a rescue flight could reach them in days. The distance between that isolation and Proxima B is not measurable on any scale that applies to human experience. Every other mission in human history has had someone on Earth who could hear them. The Antarctic winter crews that overwinter at stations like Concordia or McMurdo are among the most isolated human beings on Earth. For months, no resupply is possible. No evacuation is feasible. The crew must handle medical emergencies, equipment failures, and psychological crises with whatever they brought and whatever expertise they collectively hold. Researchers who study the psychological effects of this isolation, and they study it precisely because the parallels to space missions are real, document the mental health toll of months in a closed environment with no external contact and no rescue option. Concordia Station has satellite communication. Every crew member there can call home. Every crew member can speak with a physician in real time. Every crew member knows that in an emergency, extraordinary resources can be mobilized and someone can reach them within weeks. A Proxima B crew has none of that. The nearest analogy to their isolation that has ever existed in human experience is still separated from their actual situation by a factor of tens of thousands of years of communication delay. The psychology of that, the knowledge that no help is coming, ever, that every decision is final, has never been studied because it has never existed. The terrifying thing is not that any one of these problems is unsolved, it is that they are all unsolved at the same time, and they are not independent of each other. Consider the interactions. Improving propulsion speed reduces travel time, which reduces cumulative radiation exposure and reduces the duration over which biology degrades and social structures must hold together. This is a genuine benefit. But improving propulsion speed requires more energy, which means more fuel and more mass, which requires more propulsion energy to accelerate. Adding radiation shielding reduces the dose but adds mass, which slows the ship, which increases travel time, which increases the total dose the shielding was added to reduce. Every fix for one variable tightens the constraints on another. This is not the kind of problem where optimizing each component separately leads to an optimized whole. The variables are coupled. Solving the propulsion problem in isolation, assuming infinite shielding mass, assuming perfect life support, assuming no communication constraint, yields a theoretically workable propulsion system. Solving the radiation problem in isolation, assuming unlimited mass and power, yields a theoretically workable shielding system. But when you assemble the requirements simultaneously, they conflict. The mass the radiation system needs slows the ship the propulsion system was optimized for. The travel time the propulsion system produces determines the total radiation dose the shielding system was sized to handle. Change one, and the others must be recalculated. Engineers call this a coupled constraint problem. The most famous example in spaceflight is the rocket equation itself, the Tsiolkovsky relationship between fuel mass and vehicle velocity that means every kilogram of fuel requires more fuel to accelerate it, which requires more fuel still in an exponential spiral. An interstellar crewed mission to Proxima B is a system of coupled constraints, several of which are not engineering problems at all but fixed physical properties of the universe. The communication delay does not interact with any of this. It is determined entirely by the distance and the speed of light. Making the ship faster does not change it. A crew that arrives in 50 years still faces a 4.24-year one-way signal lag. Making the ship larger does not change it. Improving life support does not change it. The delay is not a variable in the mission design. It is a physical constant imposed by the universe. The stellar flares are fixed. They are a property of Proxima Centauri, astrophysical and ancient, predating human awareness by billions of years. The tidal locking of Proxima B is a gravitational consequence of orbital mechanics acting over 4 billion years. Neither of these things responds to mission planning, engineering ambition, or increased funding. There is a useful distinction between a problem that is very hard and a problem that is structural. A very hard problem yields, eventually, to sufficient resources and ingenuity. Engineers solve very hard problems constantly. A structural problem is one built into the arrangement of the situation, rather than into any particular technical gap. Structural problems do not dissolve with more effort. They require either a fundamentally different arrangement of the physical world, which may not be possible, or honest acceptance of the constraint. Some barriers here are engineering problems of genuine difficulty. Propulsion, life support, closed-loop recycling, these may eventually yield to technologies not yet invented. The word impossible applied to them would be overreach. But the communication delay is structural. The stellar activity is structural. The tidal locking is structural. The time required at any physically achievable speed and its consequences for human biology, that is structural. And the combination of all of them together, non-independent and mutually reinforcing, creates a total constraint that itself has the character of a structural problem. This is not pessimism. It is a description of the situation as physics currently defines it. But precision matters. We cannot currently do this is different from this cannot be done. The first is a statement about present capability. The second is a statement about physics. Most of what has been described in this script falls into the first category, engineering challenges of varying severity, some of which may yield to future technology. But some of it, the communication delay, the tidal locking, the stellar activity, falls into the second category. The speed of light is not going to increase. Proxima Centauri is not going to stop flaring. These are facts about the universe, not facts about our current state of development. Knowing the difference is not pessimism. It is the beginning of honest thinking about what the barriers actually are and which of them are worth working on. We are not failing to reach Proxima b because we have not tried hard enough. We are not failing because we lack funding or political will or courage. We are failing because every path to that planet runs through a set of physical laws that do not negotiate. The universe does not grade on effort, it grades on physics. That is not a reason to stop thinking about Proxima b. It is a reason to be precise about what thinking about it actually involves, what is an engineering problem, what is a physics constraint, and what the difference between those two categories means for how we approach the gap between here and there. What does this mean concretely for the word in the title? Impossible is sometimes used loosely to mean very difficult or not currently achievable. In that sense, many things have been impossible that are now routine. Powered flight was impossible. Reaching the moon was impossible. Sequencing the human genome was impossible. The impossibility described in this script is different in kind. It is not the impossibility of a problem that has not yet been solved. It is the impossibility of a combination of constraints, some engineering problems, some physics facts about the universe, that cannot all be satisfied simultaneously with any technology we can theorize within the bounds of known physics. A crewed mission to Proxima b requires solving propulsion, radiation, life support, biology, social cohesion, and communication delay simultaneously. The last item on that list cannot be solved. It is determined by the speed of light and the distance to the star. The others, even if all solved, and none are solved, still leave a crew at a destination they cannot call home from that may not be habitable, orbiting a star that works to strip away habitability with no way to return in any human time frame. That is the specific sense in which the word applies. And yet, look at what we actually did. A team of astronomers stood on Earth, pointed a spectrograph at a dim red star 25 trillion miles away, and measured its wobble. Not the planet, the wobble. A 1.4 meter per second gravitational tug on a distant star, detected by reading the colour of its light through a telescope in a desert. That is what the discovery of Proxima b actually was. Not a spacecraft arriving in orbit, not a probe sending back images. A group of people standing on one planet using light and mathematics to find another world, without crossing a single mile of the distance between them. Gia Manglada Eskard and his team did not leave the ground. They did not send anything. They accumulated years of spectroscopic measurements, extracted a periodic signal from the noise of stellar variability, confirmed it across multiple instruments and multiple data sets, and published a paper. The planet was 25 trillion miles away. The method worked anyway. This is not a consolation prize for the barriers described in previous chapters. It is something genuinely different. Physical access and knowledge are not the same thing. They never have been. Long before any explorer reached the far shore, cartographers drew coastlines from sailors' accounts. Ptolemy mapped territories he never visited. James Cook charted stretches of the Pacific using celestial navigation and inference before any European had walked those shores. Every map contains, at its edges, an honest statement: here is where confirmed knowledge ends, and here is what the evidence suggests beyond it. Proxima now has an entry in the catalogue of confirmed worlds. Orbital period 11.2 days. Minimum mass 1.07 Earth masses. Distance from its star 0.485 astronomical units. Position inside the habitable zone as defined by temperature geometry. Distance from Earth 24 light years. The James Webb Space Telescope is now studying nearby planetary systems with instruments more sensitive than anything previously operated. Whether the geometry of Proxima B's orbit and the activity of its host star allow useful atmospheric characterization remains uncertain, Dwest may not be able to answer these questions directly. The planet does not transit its star as seen from Earth, which eliminates the most powerful current method of atmospheric detection. Future observatories designed specifically for direct imaging of nearby Earth-sized planets, proposed missions like the Habitable Worlds Observatory, may be able to detect reflected light from Proxima B directly and analyze its spectrum for atmospheric signatures. These are real programs being seriously pursued. The instrumentation is challenging, but theoretically achievable. A generation from now, we may know whether Proxima B has an atmosphere, what it is composed of, and whether it contains chemicals that could be associated with biological processes. We will know this from instruments on Earth or in Earth orbit, without sending anything to that system. The measurement continues. The map fills in, observation by observation, without anyone leaving this planet. We cannot send a person to Proxima B. We can learn what it is made of. We can detect what gases are in its atmosphere, if any. We can track its orbit for centuries and build a picture of the system that no probe could produce without being there. Knowledge and access are different things. This distinction has always existed in human experience, and humans have always worked with both sides of it simultaneously. The cartographers who drew the coast of Africa without having been to its southern tip were not doing nothing. Their maps accumulated over decades of partial knowledge, this section confirmed, this section estimated, this section labelled with honest uncertainty, until someone finally rounded the cape. The map came first. The voyage came later, guided by what the map already contained. Astronomers are building the map of the Proxima Centauri system now. With each observation, with each telescope generation, with each improved instrument, the detail increases. We know the orbital period to 2 decimal places. We know the minimum mass within a small fraction of Earth's. Future instruments may determine whether the planet transits its star as seen from Earth, and if it does, whether absorption spectroscopy during transit reveals the chemical signature of an atmosphere, or the absence of one. The picture will be more complete before any mission of any kind reaches that system. And the picture matters regardless of whether any mission ever does. We have never crossed an ocean without knowing it was there first. There are researchers working on pieces of this right now. The Breakthrough Starshot engineering team is developing the component technologies for laser propulsion of gram-scale spacecraft, laser array coherence, light sail materials, miniaturized instrumentation for relativistic flight. The goal is not an immediate launch but a demonstrated proof of concept for each enabling technology, building toward a mission that could reach Proxima Centauri in a human lifetime, not carrying a crew but carrying a camera and a transmitter, and sending back the first direct measurements from another stellar system. NASA's Space Technology Mission Directorate maintains research programs in nuclear thermal propulsion, revisiting the 1960s NERVA technology with modern materials and updated designs. The Draco program, announced in recent years, is working toward a demonstration of nuclear thermal propulsion in orbit, a step that would represent the first new nuclear propulsion technology tested in space since the 1960s. Fusion propulsion research advances alongside fusion energy research. The same plasma physics that the National Ignition Facility's landmark fusion ignition achievement in December 2022 moved forward. Scientists at ESA and the European Southern Observatory continue refining measurements of the Proxima Centauri system and attempting atmospheric characterization of nearby exoplanets with increasing precision. This work is real. The people doing it are serious. The progress within the specific domains where progress is possible is genuine. Here is what we do not have. We do not have a propulsion system capable of accelerating a crewed spacecraft to a significant fraction of the speed of light. The fastest vehicle we have ever built travels at 430,000 miles per hour. Reaching Proxima b in a human lifetime requires something in the range of 10 to 20% of light speed, roughly 67 to 134 million miles per hour. The gap between those numbers is not a gap of engineering refinement, it is a gap of physical capability measured in orders of magnitude. We do not have a radiation shielding solution for human beings on a multi-decade interstellar mission. The galactic cosmic ray problem does not have a passive material solution at practical mass budgets. Active magnetic shielding has been proposed and studied at theoretical level. It has never been tested in space at any scale approaching mission requirements. We do not have a closed-loop life support system demonstrated to operate without external resupply for more than a few hundred days. The ISS has operated for over 25 years with continuous resupply. The gap between operates with resupply and operates without resupply is the gap between a building with a water main and a house in the desert with no well. We do not have a governance model validated for a closed human society across multiple generations. We have theories. We have historical analogies that mostly end in collapse or conflict. We do not have an existence proof. We do not have a solution to the communication delay, because the communication delay is not an engineering problem. It is determined by the distance and the speed of light, both of which are fixed. Each of these is a genuine, specific, verifiable gap, not in ambition, in demonstrated capability. This is not pessimism, it is precision. The engineers working on these problems are not failing. They are working on problems that are genuinely hard, at the edge of what current science and engineering can reach. The gaps are specific enough to be stated, which means they are specific enough to eventually be addressed. Some of them, others are fixed by the universe. But specificity is the beginning of progress. You cannot close a gap you have not clearly named. Proxima b is 4.24 light-years away. It completes another orbit tonight, as it has every 11.2 days for 4 billion years. The star is still there. The planet is still there. The address is still confirmed. This is the position the species currently occupies, in possession of an address to the nearest world beyond our solar system, equipped with a detailed understanding of every barrier between here and there, and lacking the demonstrated capability to cross any of them at the required scale. That is not a comfortable position. It is an honest one. The alternative, pretending the barriers are smaller than they are, or that progress in one area resolves constraints in others, or that eventually is a sufficient answer to specific, named, measurable gaps, does not serve the people who would need to actually close those gaps. What we do with that address, given the current state of what we know and what we can build, remains an honest question. Right now, Proxima b is completing another orbit. 11 days. A tight ellipse around a red star that flares without warning, and the planet moves through it, one face permanently lit, one face permanently dark. The terminator strip between them receiving a light that has not changed since before any animal on Earth could see. Step outside on a clear night. Find the southern sky if you can, look toward the constellation Centaurus, and understand that somewhere in the direction of one faint point of light, there is a world. Rocky, approximately our size. In a zone where temperature physics would permit water on a surface, if the atmosphere permits water at all. It is there right now. It has been there for 4 billion years without needing us to find it, and it will be there 4 billion years from now regardless of what we decide to do about the fact that we have. It is 25 trillion miles away. And we know it is there. We found it from here. With instruments on this planet, with mathematics developed by people who never left the ground, with patience, years of accumulated spectroscopic measurements, a signal extracted from noise, a wobble in a star 25 trillion miles away translated into an address. The finding is not nothing. It may be the most precise thing the species has ever done, to locate a world so completely, from such a distance, and to understand so clearly what stands between us and it. Step back and consider what kind of achievement that actually is. The planet Proxima b has been there for 4 billion years. The light leaving that system has been available to any observer with sufficient instruments for the entirety of human history. What changed in August 2016 was not the planet or the light. It was the precision of our instruments, the patience of the team that used them, and the mathematics that allowed a periodic 1.4 meter per second wobble to be distinguished from the background noise of stellar activity. We didn't go to Proxima b. We reached out with our understanding across 25 trillion miles and found it where it has always been. That is a different kind of arrival, but it is not nothing. It is, in its own way, the most human thing possible. To know a place completely, in all its inhospitable specificity, and to know exactly why we cannot go there. To map the currently impassable with precision, to name the unreachable without pretending it is reachable. To hold both the wonder of the finding and the weight of the distance at the same time, without letting either one erase the other. The barriers are real. The communication silence is real. The biology is real. The physics of mass and velocity and time do not bend for human ambition. The universe is under no obligation to be reachable by the creatures that evolved on one of its smaller rocks. And yet those creatures looked up, and looked precisely enough, and found the address. The planet does not wait. It orbits on its schedule, indifferent to whether anything in its system is alive, indifferent to whether anything 25 trillion miles away has noticed it, or built instruments capable of detecting its presence or written papers about what it might be like to stand on its terminator in that unmoving half-light. We noticed. We measured. We named it. There is a specific kind of pride available in that, separate from the pride of reaching something. The person who first measures a mountain that no one has climbed yet, who triangulates its height from the valley floor, who calculates with sufficient precision that others trust the number, has done something real. The mountain is still unclimbed. The measurement is still an achievement. Proxima b was unmapped territory until 2016. Now it has an address, an orbital period, a mass estimate, a position in the habitable zone catalogue, and a steadily growing body of observational data. The people who produced those numbers were doing science in the full sense, converting ignorance into knowledge precisely and verifiably from here without going there. That knowledge, once established, is permanent. It does not expire. Whatever happens in the next decade or the next century of astronomy, Proxima b will remain the closest confirmed world beyond our solar system, measured by people standing on this planet using instruments we built through methods we invented. The measurement may be refined over time. The picture of the planet may grow clearer. The barriers may narrow in ways we cannot currently predict. But the fact of the finding and the fact of what was found belongs to this moment in history, to this specific generation of astronomers who had just enough precision to extract a walking pace wobble from a distant star and know with confidence that something real was there. That is the other half of impossible. The planet is real. The distance is real. The barriers are real. And the fact that we know all three of these things with the precision we know them from the single planet we inhabit, that is real too. We stand here on a rocky world orbiting a quiet and unremarkable yellow star, and we know the address of another world, and we know the exact weight of every wall between us and it. The knowledge cost us nothing but patience, time, and precision. The distance costs us everything else. Both of these remain true simultaneously. The universe arranges things that way, not to frustrate, but simply because it does not arrange itself around us. If you found tonight useful, if these are the questions you want to keep sitting with, like the video or subscribe. There is more of this. Good night.